Alright, what I want to look at here is what's called a reflection grating, and it has come up in scholarship. Probably come up in level 3 if I look far enough back. But anyway, what we've got here is a situation where we've got two rays coming in, being reflected, and off this grating. Okay, so this grating's got areas that it can reflect from, but it is a grating with gaps, so it can reflect here or here. So we've got this space, and I'm going to call that space, or that distance, d. So it's a little like this whole diffraction episode we've been doing, and we want to see where are those waves going to be in phase, where are they not going to be in phase. So it's that whole path difference idea yet again. Now we've got, if we split that into 90 degrees, then they usually are made to be 90 degrees. We'll call that theta in, and we could call that anything we like. If we called it I, for example, usually theta I and I plus I will equal 90 degrees, but they are not necessarily equal. Okay, so we can call that a blazed grating if you like, but they are chosen so that theta and I equal 90 degrees. Now what we want to do with this little situation here is work out what's actually going to happen, and what we find is we're going to be looking at path differences here. So at this point here, they're both gone the same distance, so they'd be in phase, right? These two waves. But this one's now going to travel down here before it goes off that way, and this one's going to travel up here. So the difference between this distance here and this distance here is the path difference we're talking about. And I can call this distance here, if you like, x, and this distance here, y. Right, now we just need to do a little bit of trigonometry and figure out what that difference, what that path difference actually is. And so we've got these angles, and what we need to know is which ones are which. So I called that theta in. I need to have defined a theta out. I'll call my theta out this angle. Alright, so that's my theta out. I should get a little hard, theta with an O. Alright, now if we're going to try and figure out the path difference between y and x, we can do that by realizing that theta I, this is also theta I there, and this one over in the corner here is also theta out. So we can do basic trigonometry and say x, this side here, is going to be equal to d times the cos, because d is this whole length here, times the cos of theta I. And we can say that y is going to be equal to d times the cos of theta out. Right? So we can actually see that, and theta in doesn't necessarily equal theta out. This is not the same as what we're used to. We can say that the path difference then is going to be equal to d times the cos of theta in minus cos of theta out. Right? Pretty obvious. We're just subtracting two lengths, y and x. Now, if we want constructive interference, then that's going to happen at n wavelengths. So you can see we can get a whole bunch of different angles here. I've just done those, and we're figuring out which angle this whole thing works for. And it's called a reflection grating.